We want to find the center of mass of a lamina as pictured below, with inner radius 4 and outer radius 5, with the given density function sigma of x comma y. To find the center of mass, we need to find x bar comma y bar, but before we can find the center of mass, we need to find the mass given by this double integral, the moment about the x-axis given by this double integral, and the moment about the y-axis given by this double integral. Notice for the mass, the integrand function is the density function. For the moment about the x-axis, the integrand function is y times the density function. And for the moment about the y-axis, the integrand function is x times the density function. So we'll first set up these three double integrals, evaluate them, and then we'll find the center of mass. But because our region of integration here is bounded between two circles in the first quadrant, we're going to use polar coordinates rather than rectangular coordinates. So for our first step, let's rewrite the density function as a function of r and theta. So sigma of r comma theta would be equal to, well, x is equal to r cosine theta, and x squared plus y squared is equal to r squared. So we have r cosine theta divided by r squared, which simplifies to cosine theta divided by r. Which means for the mass, we're going to have the double integral. Again, in polar form, we'll have f of r comma theta, which is cosine theta, divided by r. Then remember, for polar coordinates, differential a is equal to r dr d theta. Don't forget this extra factor of r when converting from rectangular to polar coordinates. And then here the r's simplify. So the integrand function is just cosine theta. And now we need to find the limits of integration for r and theta. Remember, r is the radius, and we're told the inner radius is 4, and the outer radius is 5, which means the limits of integration for r would be from 4 to 5. And then for angle theta, because we're in the first quadrant, it would be theta equals 0 to theta equals pi divided by 2. So this gives us the double integral of cosine theta dr d theta. The limits of integration for r are from 4 to 5, and for theta, they're from 0 to pi divided by 2. Now for the moment about the x-axis, it's going to be similar, except notice how we have this extra factor of y in the integrand function. So the region of integration is going to be the same. But now the integrand function is going to be y times the density function. Well, y is equal to r sine theta. So we'll have r sine theta. And then times the density function, which we know is cosine theta divided by r. And again, we have r dr d theta. So this simplifies to 1. So the moment about the x-axis is equal to a double integral over the region R. And the integrated function is going to be r sine theta cosine theta dr d theta. And now we'll set up the moment about the y-axis. Again, the region of integration is going to be the same. X is equal to r cosine theta, so we have r cosine theta times the density function, which is cosine theta divided by r, and then r dr d theta. Simplifying again, we have the double integral over the region R. We have r cosine squared theta as the integrand function, dr d theta. We now need to evaluate each of these double integrals. So for the mass, we first integrate with respect to r, treating cosine theta as a constant. So we have the integral from 0 to pi over 2 of r cosine theta. Get the limits of integration for r from 4 to 5. So when r is equal to 5, we have 5 cosine theta. And when r is equal to 4, we have minus 4 cosine theta. So this simplifies nicely to the integral from 0 to pi divided by 2 of just 1 cosine theta, or cosine theta. Now we integrate respect to theta, giving us sine theta. So we have sine pi divided by 2 minus sine 0, which is equal to 1 minus 0, which equals 1. So now we know the mass is equal to 1. Let's go ahead and write this back on the first slide. So we know the mass is equal to 1. And now let's find the moment about the x-axis by evaluating this double integral. So we first integrate with respect to r. So we'd have r squared divided by 2 times sine theta cosine theta, or 1/2 r squared sine theta cosine theta. So when r is equal to 5, we'd have 25 halves sine theta cosine theta. And then when r is 4, we'd have 16 halves, which I know is equal to 8. This will make it easier to find the difference. Sine theta cosine theta. So 25 halves minus 16 halves would be 9 halves. So this simplifies to the integral from 0 to pi divided by 2 of 9 halves sine theta cosine theta. Now from here we'll perform u substitution. Because the derivative of sine is cosine, we'll let u equal sine theta. And therefore differential u is equal to cosine theta d theta. So in terms of u, all of this would just be u du. So the antiderivative with respect to u would just be u squared divided by 2, or 1/2 u squared, but u squared is really sine squared theta. So here we'll have 9/4 times, when theta is pi divided by 2, we have sine, I'm going to write this as sine pi divided by 2 squared minus sine 0 squared, which is equal to 9/4. And sine pi over 2 is equal to 1, so we have 1 squared minus sine 0 is 0, so we just have 1 squared minus 0 squared, which is just equal to 1, which equals 9/4. So now we know the moment about the x-axis is equal to 9/4. Again, let's go ahead and record this on the first slide. And now we need to find the moment about the y-axis. To do this, we'll evaluate this double integral here. So we first integrate with respect to r, which will give us r squared divided by 2 times cosine squared theta. Or if we want 1/2 r squared cosine squared theta. So when r is equal to 5, we have 25 halves cosine squared theta, minus when r is 4, we have 16 halves cosine squared theta. 25 halves minus 16 halves is 9 halves. So we have the integral from 0 to pi divided by 2 of 9 halves cosine squared theta d theta. From here we'll perform a substitution for cosine squared theta, where cosine squared theta is equal to 1/2 times the quantity 1 plus cosine 2 theta. Because we already have 9 halves here, 9 halves times 1/2 would be 9/4. So we have 9/4 times integral from 0 to pi divided by 2 of just 1 plus cosine 2 theta d theta. And now we integrate with respect to theta. So we'll have 9/4, and the antiderivative of 1 will be theta. And now to find the antiderivative of cosine 2 theta, we have to perform u substitution. So we'd have u equal to 2 theta. Differential u is equal to 2 d theta. So notice how if we divide both sides by 2, d theta is equal to 1/2 du. So we can think of cosine 2 theta d theta as 1/2 cosine u du, which means the antiderivative in terms of theta would be 1/2 sine u, or sine 2 theta. So when theta is equal to pi divided by 2, we have pi divided by 2 plus 1/2 sine 2 theta would be 2 times pi divided by 2, which would be pi, minus, when theta is 0, we have 0 minus 1/2 sine 0. Well, sine pi is equal to 0, and sine 0 is also 0, so this just simplifies to 9/4 times pi divided by 2, which equals 9 pi divided by 8. So now we finally have the moment about the y-axis, and now we can find the center of mass. And again, the x-coordinate of the center of mass is equal to the moment about the y-axis divided by the mass, and the y-coordinate of the center of mass is equal to the moment about the x-axis divided by the mass, which means x bar is equal to, again, the moment about the y-axis divided by the mass, which is equal to 9 pi divided by 8 divided by 1, which is just 9 pi divided by 8. And the y-coordinate of the center of mass, or y bar, is equal to the moment about the x-axis divided by the mass, which would be equal to 9/4 divided by 1, which is, of course is just 9/4. So x bar, again, is 9 pi divided by 8, and y bar is 9/4. Let's also convert these to decimals. X bar is approximately 3.5343, and 9/4 is 2.25. I hope you found this helpful.